This is Jack Jackson. In this video we're going to go over the basic shortcut properties of derivatives, and these are things that we have been deriving in this and using in this playlist and in these notes that go along with it. So except for the portions in blue, I expect my students to memorize everything that you're going to see on this particular video. These are all things we've worked at before, and let's go through this. So below, f, g, u, and v are functions of x, so as x changes, they change. So perhaps there have been some substitution. B and n are constants, and I've integrated the use of the chain rule pretty much throughout. So we've got a couple of different categories of derivative properties. The first category here is, I'm going to label it rewriting in terms of other derivatives. So what we have here is a list of properties, and these properties do not actually compute a derivative all the way. What they do is they rewrite a derivative in terms of one or more other derivatives. And so this allows us to hopefully break a more complicated problem down into something a little bit simpler. Okay, so the first one is the sum rule. The sum rule says the derivative of the sum is the sum of the derivatives. The derivative of f of x plus g of x is f prime of x plus g prime of x. So you can take the derivative of each part there. The constant multiple rule says the derivative of a constant times the function is a constant times derivative function. But alas, the derivative product is not the product of the derivatives. It's a little more complicated. The derivative of f of x times g of x is f of x times g prime of x plus g of x times f prime of x. So if you have two factors, I usually do it in this order. I take the first factor times the derivative of the second factor plus the second factor times the derivative of the first factor. There are a couple of other orders you may do this in. Because multiplication is commutative, you could switch these two first factors or the second two, and addition is commutative, so you could switch those two terms. In fact, I do switch it a little bit if I have more than two terms. So, for example, this generalizes to more products. So, for example, if you have a product of three factors, you can take the derivative of the first factor times the other two factors, plus the derivative of the second factor times the other two, plus the derivative of the third factor times the other two. Or, more generally, if you have the derivative of a product of however many factors you might have, any finite number of factors, you take the derivative of the first factor times all the other factors, plus the derivative of the second factor times all the other factors, plus the derivative of the third times all the other factors, plus the derivative of the fourth times all the other factors, and so on until you run out of factors. So you'll have one term for every factor that you start with, and each one of those terms is a bunch of things multiplied together, with one of them being a derivative and not the others. And that's what's meant by this blue notation here of utilizing product and summation notation. Let's go on. And once again, you should always go back to the earlier videos to see how we derived and proved all these properties and also how we have used them. So the quotient rule says the derivative of f of x over g of x is g of x times f prime of x minus f of x times g prime of x over g of x squared. Okay, so if you have two factors here, in a quotient, it's the bottom factor times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Now the chain rule, here's a couple of different ways of writing it. I usually think of it more in terms of this last way here. So this could also be called the composition rule or the substitution rule. So if we do some substitution where u is a function of x and rewrite the original function, which was in terms of x, as a function of u, then we take the derivative of that with respect to u and evaluate it at u, but then we also multiply by the derivative of u with respect to the original x. So the chain rule sort of permeates everything else often, and we're going to see the stuff below will be all rewritten in terms of the chain rule. Now we also have an inverse function rule, the derivative of f inverse of x. So this last way of writing is probably a better way. What it shows here is if you take the derivative of f inverse of x, what you get is 1 over the derivative of f of u with respect to u, evaluated where u... Okay, moving on. we have derivatives of basic functions from algebra, and I've incorporated the chain rule here. So derivative of constant functions is 0. Derivative of a linear function like c times x is just c. And we have a generalized version of the power exponential rule. So the derivative of u to the v, where both u and v are functions of x, is first you take the, that's typo, it should say v times u to the v minus 1. So take the old power down, subtract 1 from the old power, and take the derivative of the base. Plus, you take the natural logarithm of base times the original thing, and that should say u to the v, times the derivative of the power v. Now, of course, if these are both constants, then both of these little derivatives here are 0, and of course we have the derivative constant 0. If the v is a constant, then the derivative of v is 0, and the second term goes away, and what we have is just the first term, which is the power rule. So the derivative of, say, u to the n, where n is a constant, is n times u to the n minus 1 times the derivative of the u. On the other hand, if the u is a constant up here, this first part, the derivative is 0 here, and so this goes away, and we have this part right here, the second term, which is the exponential function. So if b is a constant, the derivative of b to the u is natural log of b times b to the u times the derivative of the u. A special case of that is the derivative of e to the u is e to the u times the derivative of the u, because of the natural log of e, of course, is 1. The derivative of the logarithm of the absolute value of u is 1 over u times the derivative of the u. And the derivative of natural log of u is, without the absolute value, is also 1 over u times the derivative of u, but this only applies when u is a positive number. Again, should memorize all those. And if we're just taking a survey of calculus, that's where we would probably stop. For Calculus 1 students, we're going to go on and look at some other functions here. Okay, first of all, the derivatives of the basic trigonometric functions. We need to memorize those here. Derivative of sine of u is cosine of u times the derivative of the u. Derivative of tangent of u is secant square of u times the derivative of the u. And derivative of secant u is secant u times tangent of u times the derivative of the u. Now, all the ones that start with the co here have a negative in front, and then there's the cofunctions from over here. So derivative of sine is cosine. Derivative of cosine is minus sine. So derivative of cosine of u is minus, or the opposite of sine of u times the derivative of u. Derivative of tangent u is secant square of u, so derivative of cotangent of u is the opposite of cosecant square of u du. And derivative of secant u is secant u tangent u, so derivative of cosecant u is minus cosecant u cotangent u derivative of u. Now, hyperbolic trig functions, really I'm mainly interested in just memorizing the first two of those. The derivative of sinh of u is cosh of u, and derivative of cosh of u is sinh of u. But we also have derived some of these other properties in the last couple of videos. So the derivative of hyperbolic tangent of u is hyperbolic secant square of u, very much like the derivative of tangent u is secant square of u. Derivative of hyperbolic secant of u is the opposite of hyperbolic secant of u, hyperbolic tangent of u, du, just like the derivative of secant u is secant u tangent u, but notice there's a negative here that you didn't have up here. In the regular trig functions, it's real easy to remember which ones have a negative. All the ones that start with co have, start with a c, they have a negative. Okay, over here, derivative of cosh is sinh, no minus. Like up here we had derivative of cosine was sine with a negative, but over here no negative. Derivative of coth, or hyperbolic cotangent of u, is the opposite of cosecant square of u du, very similar to that one. And the derivative of hyperbolic cosecant of u is minus cosecant of u times hyperbolic cotangent, minus hyperbolic cosecant of u times hyperbolic cotangent of u times du, very much like this one. So these are very similar. If you know these for circular trig functions, you can pretty much get these for hyperbolic trig functions. You just have to kind of remember where the minus signs go, and it's a little bit different here. Derivative of sinh is cosh, derivative of cosh is sinh, no minuses there. And then in both cases you get three negatives. Up here, the ones that start with co are all the ones that are negative. Down here, it's these three right here that have a negative in front. Now we get to inverse trig functions. At least two of those I'd like you to memorize. The derivative of inverse sine of u is 1 over the square root of 1 minus u squared times du over dx. And the derivative of inverse tangent of u is 1 over u squared plus 1 du over dx. I probably should have written that as arc sine of u and arc tangent of u, because that's really a better way to write it. But this is the way you'd probably write them in your calculator. The derivative of the arc secant of u is 1 over the absolute value of u times the square root of u squared minus 1 times du over dx. And once again, the ones that start with co have a negative, and they're just the opposites of what we have here. Derivative inverse sine is 1 over square root of 1 minus u squared du over dx, and the derivative of inverse cosine of u, arc cosine of u, is negative 1 over square root of 1 minus u squared du over dx. And derivative of arc tangent is 1 over u squared plus 1. The derivative of arc cotangent is minus 1 over u squared plus 1. Of course, both of those have times du over dx. All of these I'm putting a u here, which is a function of x, so I'm saying this is what you get after you've done a substitution, perhaps, and you have to multiply by the du over dx. Of course, if the u is just 1, if the u is just x, then du over dx is just 1, and you can leave that out, of course. And finally, we can see the one here for inverse cosecant. And finally, we have a list of some properties that we did for inverse hyperbolic functions, and I don't necessarily need my students to have these memorized. But we did derive these. I'll get back up here. And here you see these. The inverse hyperbolic secant of x is 1 over square root of x squared plus 1. Derivative of cosh inverse of x is 1 over x square root of x squared minus 1. And this must be only x is greater than or equal to, actually just greater than 1, period. Not even equal to, strictly greater than. But the one for hyperbolic sine inverse sinh, is valid for all x's. Inverse hyperbolic tangent is 1 over 1 minus x squared, and it's implied in the formula that x has to be between negative 1 and 1. No, it doesn't. It's not implied in the formula. But that is part of it. It may need to have that. Implied in the formula that x is not negative 1 or 1. In the formula, it could be outside of that, bigger than 1 or less than negative 1, but that's not allowed because of the inverse tangent. The inverse hyperbolic tangent that we're taking the derivative of is only defined here. Inverse hyperbolic cosecant is minus 1 over absolute value of x squared, square root of x squared plus 1. Inverse hyperbolic secant here, negative 1 over x times the square root of 1 minus x squared. This is valid from 0 to 1, like this. And inverse hyperbolic cotangent is 1 over 1 minus x squared, and this is valid here. Notice that the inverse hyperbolic tangent and inverse hyperbolic cotangent have the same derivative formula, but completely different places where they're defined. Non-overlapping spots here. Inverse hyperbolic tangents defined between the asymptotes, and then this is on the outer side of both asymptotes down here. So that gives you a complete list of the basic formulas that we have derived, and we've looked at many examples here. In the next video, we'll look at a few more examples of using these properties.